on SolidCAM.com. Just go into webinars, webinar recordings, and you have all of the webinars that we did previously, including the last one, HSM Part 1. Just by clicking on it, it opens up on the top. You can stream it or even download the video if you want. So anyone who missed any webinar in that matter can always go into our site and view the previous webinars that we had. Okay, as I said, we'll be doing this webinar on part 2 of HSM. If there are any questions during the webinar, you can always ask your questions just by simply clicking on raise a hand, writing your question down in the question area, and then when you complete the question, just simply click on the send button over here, and at the end of the webinar, I'll go through the questions and answer them to the best of my ability. Okay, as I said, we'll be continuing where we left off last time on HSM, and I'd like to go to our next few options that we have in HSM. And the first one I'd like to go into is called Morph machining. Now, what I'd like to do on the part, just one moment, kiss. What I'd like to do on the part is machine this area over here, this entire area inside over here. But note, we have this shape that starts at the beginning of this area and this shape at the end of that area. I'd like to work parallel to this, but however, when it gets towards this side, I want it to change slowly to be parallel to this shape over here. So we'll start our first operation, and don't forget, by the way, this webinar is being recorded. If we go into our operation of HSM, I'll use the option of morphed machining, as shown over here. I'm going to use, my geometry is target that's put there automatically. And if we go into tools, I'm going to use a 6mm ball and mill, as shown over here. Now we have our drive boundaries and we have our constraint boundaries. Our drive boundaries is basically the boundary that defines the shape of our tool path that's going to be created. So since I want to have a morphed, which goes from one curve to another curve, we have our first curve and our second curve here. We'll choose our first curve, and I'm going to choose this curve. And I'll accept it. And my second curve is going to be this curve over here. Note that the direction should be both in the same direction. In both cases, I started from this end going towards there. Okay, accept that chain. We have our constraint bound. Oh, before we do that, we have our drive boundaries. We have another option over here, whether to work along, in other words, parallel to the curves that we chose, toward the drive boundaries, or we can work across, which works actually perpendicular to the drive boundaries. Okay, I'm going to leave it at along, and we'll go into our constraint boundaries. Our constraint boundaries is basically just where do you want to work on the part. Now, this particular case, the way it is right now, I'm just going to take the entire part automatically. It'll anyway work only maximum between these two boundaries, drive boundaries over here. Let's go into passes, and I'll just give it a quick step over of every 2 millimeters. And in my link area, I'm just going to go bidirectional. We'll run our calculation and simulate the part. And if you take a look, and I'll try to do this a little bit slow, you'll see our tool path goes back and forth on the part. At this point, it's parallel to this curve over here. But as it gets closer to this curve over here, let me speed it up now, you're going to see that it's actually starting to change its shape. Let's take a look at the top. Now it's starting to change the shape more towards this shape itself. And it gets to that exact shape by the end of the day. In other words, by the end of the toolpath, it's exactly on that shape. Now, by the way, when I said every 2 millimeter step over, every 2 millimeters is the step over at its widest point. Not over here. This is the thinnest. In this particular case, this is the widest area. So it goes according to whatever the widest area is. Okay. Now, let's go back to the issue of constraint boundaries. Just to show you exactly what the constraint boundary actually does, I mean, what we saw over here is that basically it worked in here, no matter what, since even if I had the entire part as my constraint boundaries. Well, to show you exactly how the constraint boundaries work over here, let's create one manually. And I'm going to use this circle over here as my boundary. In other words, I only want it to work within that area over there. We'll accept it. Okay. Let's do save and calculate and simulate. Now what you're going to see is very simple. It works in between and within this boundary only. However, note the shape. The shape is the shape as if we took this entire part over here, the way the toolpath would have been. This is an exact cutout of the shape of that toolpath. Note that it's going actually parallel to this edge, and slowly it's changing over to this edge over there. However, it's only working within that area. Okay. Now, another option I'd like to show you on this part is something called offset. Offset is very similar in the way it works as in the Morph. However, offset, you only give it one drive boundary, and it works offset from that drive boundary in a specific direction. Let's just take a look. Let me just open up this previous operation, do save and copy, and I'll change this operation to what we call offset cutting. Now in offset cutting, I'm going to use the same tool in this particular case. Again, we have a drive boundary, but this time we're only using one curve. Let's use this curve over here, that one line over there. Okay? Note, this is the right side, this is the left side, according to the arrow over there. Now, we can work, now as you see, we can work either right, left, or in both directions. Let's work right now in the right direction. Or, you know what, let's work actually in the left direction. I want to go down towards the end over there. Now, we can either work along. No, if this is my line that I chose over there, it works along that line. Or, again, we can work across. Let's leave it at along for now. In our constraint boundaries, I'm going to use the entire part. And in my passes area, note we have the following. We have our left clear offset. If I can put in a value over here of what my left clear offset is, or I can actually take it from the part by clicking on a button and say, let's just click on this line over there. So that's going to be my clear offset. Now, how much to step over every single time? Let's step over every 2 millimeters. And in my link, we're going to go bidirectional. Let's run our simulation after it finishes the calculation. And you'll note that the tool goes back and forth starting from this end over here. Let's just take a top view, do this a little slower. From this end all the way up to here. Now, if I wanted to start from here instead of here, all I'd have to do is go into my link and just reverse the order. By reversing the order, You'll note this time it started from this side going this way. Okay, now let's go back for a moment into my drive boundaries, and instead of left, this time we're going to do both, to go in both directions. Let's go back now to our passes. Now besides our left clear offset, we now also have the right clear offset. Let me just give it a value of 30 millimeters, and we'll take a look at what we have. If we take a look at the toolpath, you'll note that it starts from one end and goes directly to the end over here. In other words, it doesn't start from here till this point over here and then start from the other side over here, going from the outside towards the actual geometry itself. It just continues one straight continuous toolpath from the beginning to the end. Now, just one more thing with this operation. If I go back to my drive boundaries, we also have across. Let's just run the simulation using the option of across. And you see this time it's going back and forth in this direction over here. Okay. Now let's go to another part. And we'll use this part over here. Now, the part that what I'd like to do on this part is to machine this area over here. Now, when I machine this area, I like to control the shape of my tool paths. In other words, I like the tool path to be with the exact same shape of this boss over here as shown over here. Let's start the operation of HSM, and we use the option of 3D constant step over. What exactly is 3D constant step over? Well, let's first go back and see what is linear. When we tell a linear to step over, let's say, for example, every millimeter, so it'll do exactly that. If you look from the top, it will step over exactly every millimeter, and it'll look very even. However, if you're working on a surface that has a curve on it, such as this one over here, when you tell it to move over every millimeter, from the top view it looks even, but as it goes down on the surface, since it's a 3D surface, it works itself further away each time. In other words, the step on the part itself is further and further away from each other, so you're not going to get a really nice cut. What 3D constant step over does, it doesn't measure each step over 1 millimeter, for example, from the top view, but rather from the 3D surface itself. It takes a measurement on the surface, 1, 2, 3, exactly according to the surface itself. So the tool pass will be very, very even along the part. Let's take a look. We'll continue on with the part, and we'll see that actually happening. I'll choose a tool, a 6 millimeter end mill. And we have here also a drive boundary and constraint boundaries. Now, drive boundaries in general, what it does is it gives you the power to choose the type of choose the shape of your tool path. For example, I created this before, so I'll make it a little easier. If my drive boundaries was this circle as shown over here, okay, that means that's the shape I want my tool path to be. Okay? My constraint boundaries, in this particular case, I want to use constraint boundary that's around the actual part over here, around the actual stub. That's the actual shape, that's the actual boundary that I wanted to work on. So for now, just to show you how this works, I'm going to want a circular tool path, but on this entire part. We'll go into our passes. We'll leave it at every 2 millimeters to go a little quicker. And if we go into our links, we have an option of one direction, bidirectional. All of these are available to us. Let's just take a quick look at our simulation. By the way, what you see here now, if I didn't mention this before, I'll mention this again, is that the calculation is being done in parallel. There are several calculations that are being done in each operation. So it's done parallel now using the multi-core of your computer. So it goes a little quicker. Okay, now let's see exactly from the top view how our tool path is going to look. Note that it takes the shape of the circle, but it actually does machine the entire part, as shown over here. The circle shape, since the circle shape continues over here and there's not nothing to cut, so it goes up in the air and then goes back and forth. And then but you have the shape exactly according to that circle. Now, like I said though, I'd like to have the shape according to the shape of the stub itself. So what I'm going to do here is go back to my dry boundary, and I'm going to use the exact same boundary as I have in my constraint boundaries. Let's take a look now at the simulation when it finishes calculating this operation. And you'll see that now it works according to the shape of that stub itself. Okay, now note the steps over here looks like it's getting closer and closer and closer to each other. But if we start looking at actually around the part, you see that the tool path is actually evenly spaced on the surface itself, on the 3D surface. Now, you may have noticed as I'm turning this around, if not, then I'll mention it to you, you'll see that the tool did not go all the way down. Well, there is a good reason for that. The reason for that is simple. Taking a look at our constraint boundaries and our dry boundaries, more on our constraint boundaries in fact, we have the tool going to the center of our boundary. So if it's going to the center, when I'm standing in the center of the tool over this, it can't go past the center of the tool, so therefore it can't go further out. And because of that, it can't go further down on the part as well. So let's change our boundary tool relation to tangent. The same thing with our dry boundaries to tangent. What's going to happen is now that it goes up until it's tangent with the next surface. Let's take a look at the simulation when we finish the calculation over here. And this time you'll see that when it goes down, it does the shape as I showed you over here. But this time it's going to go all the way down to the end over there, as shown over there. Milling out exactly up until it reaches tangent to the next surface. Okay. Now I want to load another part. And remember what I said here about it taking on the shape that I wanted it to take. The reason why I'm reminding you of this again, because in a moment we're going to talk about this in a different operation. Okay, we'll close this part. And we'll load another part that looks like this. Now, what I'd like to do in this part is to work only within this area. Now, the first operation I'd like to do is called pencil milling. What exactly is pencil milling? Well, picture a pencil that actually goes on an edge. If I were to hold a pencil up against this wall over here and go around, it'll actually have like one line over here. The same thing with any one of these walls on the part. Okay, so let's see how we can use this. We'll start an HSM operation of pencil milling. I'm going to use a 4mm ball and mill. And if I go into my constraint boundaries, I'm going to work only within this area. I created a boundary over there by user-defined boundary. Now, note if we go into our passes, there is no step over, step down, or anything. This is a single tool path on a boundary. Now, let's look. Obviously, we always have a wall offset and floor offset. But let's look now at these two options, over thickness and bitangency angle. Actually, over thickness, remember that because we're going to go back to it in a minute. We're going to skip over to bitangency angle and then in a moment go back to over thickness. What exactly is bitangency angle? Bitangency angle, if we take a look at the diagram over here, you'll note that a tool, when it comes in contact between a wall and a floor area, you have two contact points. This one over here and this one on the wall itself. Between these 2 points, an angle is formed, as shown over there. Now, if the value of this angle is 20 degrees or more, he will create a tool path exactly on that border. If it's less than 20 degrees, then it won't create a tool path. So many times you may have a floor or something like that where there's a very, very slight inclination at one point. It may not be, so if you did a pencil pass over there, you may not even feel anything. You may not have any effect on it at all. So you may say, you know what, let's skip over. We really don't need a pencil pass in that point. If you want, you can always make it lower. So let's make this right now at 15 degrees. Note I did over thickness of 0, and I'll get back to that in a moment. We'll run our calculation on the part. And what it's doing right now is checking all the areas where the tool is within that limit that I said, more than 20 degrees, 15 degrees on the part, and it's creating a tool path around there at this point. And we'll see that in a moment in our simulation. You'll see that the tool goes down and creates a tool path in the part. But wait, as you noticed already, just like I did, it only worked in certain areas. It worked over here. It worked on these corners over here, but it did not work in this area over here. It did not work anywhere around here itself, and it did not work here as well. Well, there's a good reason for that. The tool that I'm using right now is a 4mm ball end mill. That means the radius on the tool is R2. Now, I happen to know that the radius on these areas over here is larger than R2. So, in essence, when it gets to this point, it looks at its second contact point area, and since this radius is smaller than this radius over here, there is no, it's practically zero, the bitangency angle. Practically zero. Therefore, it did not create a tool path. But in any case, I want to actually have it that it does create a tool path on this area. So what I can do, and we'll go back to our operation, is we have something called over thickness. By over thickness, I'm actually making the program, think that the tool is larger for calculation purposes. The actual tool path will be on the boundary itself. Let's take a look what happens now if I were to give an over thickness to make the tool as if it's thicker so that it does touch the side. Let's give it an over thickness of 6mm and do our calculation again. Now let's see what happens when we have a tool path. Whether we get the tool path on the entire part, on all of the areas, or just in several areas. Okay, we're finishing our calculation over here. Okay, again, note the parallel calculation, the multi-core calculation that's being done over here. If we take a look now at our toolpath, you'll note this time a toolpath is created on every single one of those edges as shown over here. Because we made the program think as if the tool is larger, so it does touch that. But in essence, it really doesn't. Okay. Let's continue now with something very similar to this. However, instead of pencil milling, we're going to use the option of parallel pencil milling. Parallel pencil milling is the exact same thing as pencil milling, with one addition. And that addition is as follows. Let's go into our pencil passes. We'll do it exactly what we had before. Oversize, over thickness 6. Put that at 15. We've added in passes over here the option of saying I want to go off this to the side a little bit on both sides. Say a step over of every, leave it at 1 millimeter. And I want to have a total of 5 step overs in each direction. Let's take a look now at the simulation after it finishes the calculation itself. Again, note the multi-core calculation of HSM. Now remember, it's not only calculating this time the areas where it's supposed to machine, but it's also adding on to that the amount of step overs, which each one has its own tool path that it's taking on the part itself. We'll be done here in a moment. Okay, it's almost finished here. We'll run our simulation, and you'll see that it works in this area and in this area, just like in pencil milling. However, it works now with an offset in each direction of 1 millimeter each step, 5 times. If we take a closer look at the simulation itself, at the toolpath that was formed, let me just zoom in to this area. You'll note I said 5 steps in total in each direction. We have 1, 2, 3, 4, 5. Remember this one in a moment. We'll go down from the other side. 1, 2, 3, 4, 5. And this one is the actual pencil milling toolpath that's done. We have the pencil milling toolpath plus 5 step overs in each direction. Now, let's do one more operation here. And this operation is called 3D corner offset. Now, what exactly is 3D corner offset? If you remember from before, in our previous part, we had something called 3D constant step over. Whereas in 3D constant step over, it moves over evenly, really nicely on the surfaces, because it measures it according to the 3D surface itself. However, I had to tell it what the shape I wanted on the part to be, as far as the shape of the toolpath. In this option, 3D corner offset, instead of me creating drive boundaries, like I had to do with the previous operation, it'll take the pencil passes that's created automatically and give you the shape according to the boundaries of the pencil pad machining. Now, we have our pencil passes. I'm going to leave this at 0 for a moment. Okay? And if we go into our passes, I'll put this at every 3 millimeters. Now, it's going to work on the entire part. Okay? That I can guarantee. But the question is, what kind of shape of the toolpath will you have on the part itself? Well, remember, I'm not using a bitangency angle this time. So my borders will be not necessarily on every single edge. It will be some edges will pick up, and other edges it won't pick up because of the bitangency and because of the over thickness between the tool and the area. So let's see exactly what kind of toolpath we will get without doing the over thickness, since it does have to work on the entire area that I marked off. One more moment. if you take a look now at the simulation from the top view, you'll see it starts off in the middle as a circle, but note, since the rest of the areas could not give you a boundary from the pencil milling, it worked in those areas, but it's all working according to the shape of this area over here, this middle area over here, which it did pick up with the bitangency angle that I get it without any over thickness. Now, what I'd like it really to do is to actually work in each area according to the shape of that area. It'll also look a lot nicer. So, I'll go back to my pencil passes and use now the over thickness as I mentioned before. Now let's take a look at what kind of toolpath I'm going to get when the calculation finishes. You'll see that it'll actually be taking according to the shape of every single one of this areas. This area over here being of this shape over here, the middle area being the circle, this top area also being circle, this area as well. In other words, it'll take on the shape according to the toolpath, the pencil milling boundary that was picked up from the part, and working then 3D constant step over on those surfaces itself. We're just waiting for the calculation to finish. Okay, just one more moment. As it finishes off the calculation. By the way, this is one of the operations that the calculation does take a little longer than most other operations. Okay, let's take a look at the simulation now. This time you'll see that it works exactly according to the shape of the area that's on the part itself. I know a lot of mold makers that actually use this option because they prefer having the finish according to the shape of the area that they're working on over there. And this picks it up automatically and very well and very well in most cases. Now, let's load one last part. The part that I'd like to load actually looks like a very simple part, but well, let's take a look what's going on here. Honestly, it really is a simple part. What I'd like to do is mill out this pocket that's inside over there. And I'd like to use actually first a very shortly held tool in my operation of roughing. So we'll start off with HSR, and we'll use the option of HM roughing. The tool. Now let's take a look at the tool. I'm going to use actually a relatively large tool, but it's sticking out of the chuck, sticking out of its holder a really small amount. I'll use a 30 millimeter end mill, and it's only sticking out of the holder by 20 millimeters, and you can see that actually on the part. Let me actually put this now side view, and you'll note here's my tool, my holder, and if I go past this area, say down in the middle, obviously it looks like that the holder will actually hit the material itself. Let's choose a tool. There's one more factor that I did not mention to you, and that is this window over here, holder clearance. The holder clearance will automatically look at the holder as well as the tool and make sure that the holder doesn't come anything closer than what's written over here. So in essence, what's going to happen in this particular part is that the tool will go down really deep as it possibly can. And in order to avoid the holder from hitting any part of the stock material, it just moves itself further towards the middle, away from the wall itself. Let's take a look at the simulation. One moment, please. One more thing I forgot to do is if we have our constraint boundaries. In this particular case, my constraint boundary is this area around over here. I actually do want to create one, so we'll choose. Actually, I think I do have one. I've created one before. Yeah. We do show, and we can see that on the part itself over there. that's my boundary. I want to work only within that area itself. Now, my passes, I'm going to leave every 0.5 millimeter and step down every 10 millimeters. Okay, now since this is a core area, a cavity, if I were to open up my HM spiral, we have the option of cavity as well. Let's take a look at the simulation. And I want to use actually Solid Verify simulation. We'll start the simulation off. You'll note it cleans the first level over there. And now it's going down to its next level. So I'm going to stop it now. Let's take a look at the side view at this moment. You'll see that my holder is way into the part already. However, note that it's never getting close to the edges, and if it does get close, it just moves itself away so that it can go as deep as it possibly can. Let's just finish the operation itself, and you can see it did exactly what it was capable of doing without hitting the sides walls over here, the actual material that's left over here. Now, of course, I have to do a finish operation. So I have to do a rest rough operation, to mill out these areas over here. Because this is, at this point, really, is still a little bit too large for a finished cut. But I did take out a mass amount of material from here. So now I can work actually with a smaller end mill without worrying about pressure on the tool. So this time I'll do save and copy. Change this to rest roughing. And in my tool, we're going to use this time a tool that's a 12 millimeter bull nose tool, half a millimeter radius on the part itself, on the tool itself. We'll keep our boundaries and passes the same, and we'll actually make our step down and our passes, we'll make that at every 5 millimeters. Again, save and calculate. And we'll run our simulation in Solid Verify. And you see now what it's actually happening. Let me stop it now. It's working its way in on the surface and only working in these areas. In other words, this area over here did not go into. It just cleared off over here, and it's doing it at a nice even step over each time. Now at the bottom of this part, there happened to be a pocket over there. So it was picked up now with this operation. Now, let's go into our finish operation. Our finish operation, I like to work with the option of constant Z, going from this area up until this step over here. So go to HSM and use the option of constant Z machining. Now, as for our tool goes, if we were to take a ball nose end mill, we can only go down a very small amount because you want to get a decent surface, and therefore the further away each tool passes, the rougher this surface is going to be at the end. The closer, the better. Or we can use a different type of tool here. We can use a tool that's a taper end mill. A standard tool that exists all over the place, where the tool itself is actually tapered according to the measurement of the taper inside these walls over here. I'm going to choose that tool. My passes, let's go down every 10 millimeters. Because since I'm using now a tool like this one over here, we have a nice flat surface on that angle of the tool as well as the wall, thereby giving me the area taking large tool step downs. Let's take a look at the simulation. Okay, and we'll use solid verify. Note, I stopped it for a moment. It went down its first 10 millimeters. Now that it's getting towards the end of the 10 millimeters, look what happens. And I'll do this, try to do this one step at a time. It gets to its starting point, to its end point. And what's going to happen now is as follows. I'm going to start a little bit faster. Note that it's going down on the surface until it reaches its next level of 10 millimeters. Once it reaches another 10 millimeters, which in this case is already minus 20, it'll continue working now straight around the part until it gets to this point over here. We'll run it now until the very end of that area. And again, it does the exact same thing, never leaving the surface, always working on the surface itself. When it gets to the end, going down as shown over here. Now, let's stop this. First of all, as I said, though, I do want to have it go down only up until this surface over here. So we'll do that. Now, I want you to notice the approach. I'm not too thrilled with the way this is approaching, although it does not do any harm to the part itself. But let's take a look at the simulation again. And you'll see that when it got to the top, it actually helicaled its way into the surface itself. The reason for that is that if we go into our link area, we have our leads. You'll note that we have a horizontal lead of 2 millimeters with a maximum ramp angle of 10 degrees. Well, in 10 degrees with a 2 millimeter step down or lead in will only give you a series of radiuses as it's going down, like a whole bunch of little different helical motions on the part itself. Well, one thing I can do about that is instead of having 10 degrees, let's make this 80 degrees. Let's take a look now at the calculation of this part. And you'll see that this time, let me just stop it now. Go a little further. Stop. Okay. Note now the entrance looks different. It looks like it's going straight down, but it's not really going straight down. Let's take a look at it at the top. Let's see if I see the part, the entrance. Ah, yes, here it is. Okay. You'll note we can see the arc over here. However, if I turn to the side, it looks like it's actually going straight, but there's really an arc over there as shown. Now, there's another option I'd like to show you here as far as retreat, as far as approach and retreat, and that is the option of using what we call basic horizontal approach. Basic horizontal approach is very simple. Right now we were going down on the part itself, but think of a regular profile operation. After all, the constant Z is really a series of profile operations. It just picks up the profile automatically from the target. So what's happening here is as follows. Right now we're going down on the surface, but if I choose the option of basic horizontal approach, I can say, okay, you're approaching the outside like a regular approach with a lead in of 1.9 millimeters. Let's change this to 5 millimeters so we can actually see it a lot better. We'll run our calculation and simulation. And let's take a look at the top view over here, doing this one step at a time. You'll see that the tool goes in an arc, as shown over here. And if I continue, you'll see at every single level it goes out and then steps down on the outside of the part, not within the material, but it leaves the material, goes in from the outside in order to do this. And this was controlled by the option of, basic approach. Okay, we're going to end now. If there are any questions, you still have a moment to write them down. Again, I'd like to remind everyone that if you've missed a webinar, you can always go to our website, and in the area of webinars, we have webinar recordings that you can click on. Choose any of the recordings that I've done in the past, say this one for example, and you can either run it or click here to download the video itself. Okay, I'd like to first thank everyone for joining the webinar. We'll be back again next week, and we'll be doing a webinar next week starting with getting started. Of what's new in SolidCAM 2013, as we're looking for now towards releasing SP2 of SolidCAM 2013 in the middle of next week. So stay tuned for our next webinar next week, and have a nice rest of a nice day, and of course have a great weekend. Take care, and of course you will see this webinar posted on our site as well. So everyone, take care, have a great weekend, and speak to you next week.